With a coin. In normal everyday life, a coin can be either heads or it can be tails. Very simple, very boring. But in quantum mechanics, we can have special coins that are in what's called a superposition, which means that if we say we got lots of those coins, sometimes we could measure them as heads and sometimes as tails. In this case, around half of them are heads and half of them are tails. So we'd say that the coin is in a 50% superposition of heads and 50% tails. But we can have other possibilities as well. So say 75% of the time we measure heads and 75% of the time we measure tails. And this isn't the normal kind of probability that we encounter in everyday life. This is fundamental. We cannot know exactly which one is which. We just know the probabilities. But I can do something even more interesting. I can make superpositions of superpositions. Let's do a little diagram for that. So, I give you a coin, which, when you measure it on its own, gives half heads, half tails. I give you another coin, and you look at that, half the time it's heads, half the time it's tails. Simple as that. And then what you'd expect is, if you put a superposition of those two, so half the time it was the first case, which is half heads, half tails. Half the time the second case, half heads, half tails. What you'd expect is basically for the result to be the same. Half the time you measure it as tails, half the time you measure it as heads. However, what you find, very strangely, is that the coin is always heads. So there must be something going on here. We can't only use probabilities to describe exactly what this thing is doing. Because you see, interestingly, the states also have a phase, like waves. So what's happening here, basically, is that the heads are adding up, like these waves here, and the tails are cancelling out. Essentially, we can imagine it like a little arrow. The length of the arrow is the probability of measuring heads, and the angle that the arrow is at is called the phase, much like the waves. So since we can either measure heads or tails, we can draw an interesting little diagram like this as a way of representing it. And this arrow here represents what the coin is doing. So if the arrow is like this, we're always going to measure it tails. If the arrow is like this, we're always going to measure it heads. If it's like this, half the time it's heads and half the time it's tails. And if it's like this, again, half the time it's heads and half the time it's tails. But the phase is opposite. And similarly for this one, it's positive in the heads, but negative in the tails. And if any of you know complex numbers, this is why they crop up all the time in quantum mechanics, because essentially you have a probability and a phase, which complex numbers are great at describing. More than one coin. In our everyday life, we would have 4 possibilities. Heads, tails, heads, heads, tails, heads, and tails, tails. It's like with single coins, we can make superpositions of these 4 different states. So say we have half the time the first one is heads and the second square one is tails, and half the time the first one is tails and the second one is heads. That means if we measure one of the coins, then we automatically know that the other one is the opposite. And so if we did that, then we'd get a result like this. Half the time we get heads, tails, roughly, and roughly half the time we get tails, heads. You might want to ask is, what is the coin doing individually? And what we might expect is that, like before, half the time each individual coin is tails and half the time it's heads, which would sound like it would make sense. Yes, because there's nothing to stop both the coins sometimes being heads and sometimes being tails. It's not actually possible to take this state and decompose it into 2 individual coins. We have to consider them both together. That's why it's called entanglement. These two coins are now entangled together. You can't describe it properly without describing them both. Property to our coins. Again, which can be two possible values. In this case, I'm going to call them blue and green. Here we could get a green heads, a blue heads, a green tails, and a blue tails. And it would be as simple as that. So the relationship, say, could be that if a coin is heads, it's green, and if a coin is tails, it's blue, or vice versa. We can have a very interesting case where the head state is related to the superposition of the blue and green states. What that means is that if we got a bunch of the coins and we measured their head states, it would always, the heads and tails state, it would always be heads. And if we got a bunch of the coins in the same state and measured their color, half the time roughly it would be blue and half the time it would be green. Enough. If we took that same coin and it was always in the blue state when we measured the color, that would mean that half the time we would measure heads roughly and half the time we'd measure tails. So a diagram here which shows how this would work. Get some other axes to represent the blue and green cases. And if we put it like this, what that means is that if the coin is definitely going to be, say, green, half the time it's going to be heads, half the time it's going to be tails, because it's halfway between these two axes. Similarly for blue, but notice that the phase this time is different. The phase for the heads here is negative. So they are distinct states, but if we just focus on measuring heads and tails, then they'll both be equal. Similarly, if the coin is definitely heads, it's half the way between green and blue. We can just rotate this around like that. See that clearly as well. As this kind of superposition relationship, you cannot both know if it's heads or tails, and if it's green and blue at the same time. You can only know one. If you tried to measure both at the same time, it simply wouldn't work. You have to measure one and then the other, and measuring the other one will change what will happen to the other. Say you measured it as heads. That means then if you tried to measure the colour, there's a 50-50 chance it would be blue or green. Let's say it's blue. Now classically what you'd expect is that it would stay heads. All I've done is look at the colour. But now, because it's in the blue state, there's a 50% chance it could be heads or it could be tails. So then it could be tails, and we could keep repeating these measurements, and you can see that every time we do it, we get, once we become certain of one, we become completely uncertain in the other. Things change over time. So if we take our state here, and we get our basis, this state can change over time. So it could say it could go from being tails to being heads. But there's a few important properties that it has. One is that it can't just jump from being tails to heads. It has to go smoothly like this. Another thing is that we can't change it such that the heads and the tails state go together. They have to always remain distinct like this. So any change must preserve that angle between them. And of course, we can't change the length of this, because that would be changing the probability over time. And the probability of measuring either heads or tails always has to be 1. It always has to be a 100% chance of measuring at least one of them. And this kind of transformation is called unitary. So, how does things actually ever change? Well, like how when we rotate around a certain axis, there's always a certain set of states in quantum mechanics where the probabilities don't change over time. And that might sound like nothing would change, but what can change in this state is not the probability, but the phase, which basically means that these things rotate. So say the heads would rotate like this, and the tails would rotate like this. So let's say that the tails rotates at twice the speed of the heads. That means that by the time the heads has done only half a revolution, the tails will have done a full revolution. So we've essentially gone from being in this state to being in this state. So while the probability of measuring heads or tails is the same, if we go back to our blue and green example, you see the state now will have gone from here, from being definitely green, to being here, to being definitely heads. And that's essentially how things change in quantum mechanics. You can also imagine it if we go back to the wave example. We have one wave here and one wave here. And this second orange wave oscillates at twice the frequency of the first one. There's two wavelengths in one wavelength of the first one. And so essentially here, the height of these waves, which is called the amplitude, that's kind of like the probability of measuring it. Or if we imagine a sound wave, it's like the volume, how much of it that we hear. Whereas how many oscillations it has, that's the frequency. And if we add these two together, which is like creating a state which is in a superposition of the two, then we'll get a state where the amplitude changes over time, which essentially corresponds to the probability changing over time. If that made any sense, then I would highly recommend the Leonard Susskind books, The Theoretical Minimum, particularly the one on quantum mechanics, which is where I learned a lot of this stuff. And he actually explains it in an understandable way, which is very handy. So yeah, would highly recommend. Bye!